Welcome all. In this lecture, we are going to discuss about rectangular waveguide. A rectangular waveguide is a hollow metallic tube with a rectangular cross-section area. So, a rectangular waveguide is a hollow metallic tube with rectangular cross-section area. The walls of the rectangular waveguide confines the electromagnetic wave that is traveling through it and thereby guide the electromagnetic wave. So, the conducting walls of guide, or we can say that waveguide, confines the electromagnetic field and thereby guides the electromagnetic wave. Because it is a waveguide, so the basic functionality of the waveguide is guiding of the electromagnetic wave that is traveling through it, that is written here. And the rectangular waveguide supports two modes, that is TE mode and TM mode only. So rectangular waveguide only supports TE mode and TM mode, but it does not support TM mode, TEM mode, sorry. Why it doesn't support TEM mode? The reason is whenever the electromagnetic wave travels longitudinally guide the waveguide, then the plane wave are reflected from wall to wall. There is an internal reflection inside the wave, and this process results in the component of either the electric field or the magnetic field in the direction of resultant wave. That's why we can say that it does not support the TEM mode. Let me write it. When the wave travels longitudinally down the guide, then in this condition the plane waves are reflected from wall of the waveguide. Since there is an internal reflection inside the waveguide, then this process results in component of electric field or magnetic field in the direction of propagation. So this process result in the component of electric field or the magnetic field in the direction of propagation of resulting wave. And due to this reason, we can say that it does not provide support for TEM mode. Now, rectangular waveguide is also used as transmission line. So, rectangular waveguide are used as transmission line. Since they are used as transmission line, therefore the power flow is in the form of electric and magnetic field only. So the power flow is in form of electric or magnetic field only. Now let us have a look at the condition for wave propagation in the rectangular waveguide. So there are basically two conditions that need to be satisfied for the wave propagation in rectangular waveguide. So according to the first condition, the cutoff wavelength, that is lambda c, should always be greater than the operating wavelength, that is lambda naught. Here lambda c is cutoff wavelength and this lambda naught is operating wavelength. Moving on to the second condition for the wave propagation in terms of frequency. So for the wave propagation, the cutoff frequency should always be less than operating frequency. So Fc denotes the cutoff frequency and F0 denotes the operating frequency. Let us discuss the next point, that is for the rectangular waveguide, TE10 mode is considered as dominant mode because it has lowest cutoff frequency. So for rectangular waveguide, TE10 mode is dominant mode. Since we discussed in the lecture of dominant mode that a dominant mode always have the lowest cutoff frequency, that's why in case of the rectangular waveguide, TE mode is the only mode that have the lowest cutoff frequency. That's why it is dominant mode. Now let us have a look at the cutoff frequency. As we have discussed in the previous lecture also, that the expression for the cutoff frequency is given as C/2 under the root m/a square plus n/b square. That's why let's calculate the cutoff frequency for this TE10 mode. So here is an example for the calculation of the cutoff frequency for TE10 10 mode. Now here we substituted the general convention as TE-MN mode, and on comparing both these two terms we conclude that here the value of M is 1 here, and on comparing the value of N we get N equals to 0 only. Now substitute the value of M and N value in this expression. So the cutoff frequency will become C over 2 under the root, in place of M we write 1 over A whole square, and in place of N we write 0, so it is nothing. So it can also be evaluated as C over 2A. So this is the cutoff frequency for TE10 mode, and it is considered as lowest cutoff frequency. That's why TE10 mode is dominant mode for rectangular waveguide. Similarly, let us have a look at the expression of cutoff wavelength for rectangular waveguide. So the cutoff wavelength is denoted by lambda c, and it is given as 2ab over under the root m square b square plus n square into a square. Here a and b are the width and the breadth of this rectangular waveguide. Now let us evaluate the cutoff wavelength for TE10 mode. So here is TE10 mode, and on comparing it with the convention of TE-MN mode we get the value of M that is equals to 1 and the value of N that is equals to 0 only. On substituting the value of M and N in this expression we get lambda c, that is nothing but equals to 2ab over under the root b square plus 0 only. So it can also be simplified as lambda c, that is equals to 2 into a. So this is the cutoff wavelength for TE10 mode, and in this way we will calculate the cutoff wavelength for any mode that is given to us. Now let us have a look at the electromagnetic wave propagation inside the waveguide. So here is the wall of rectangular waveguide. Now we know that the walls of the waveguide are made up of perfect conductors, and the perfect conductors always have the conductivity that is denoted by sigma, where sigma is equals to infinity. So the wall of the waveguide is made up of perfect conductor having conductivity equals to infinite. Let us consider here is an electromagnetic wave that enters into the waveguide, and whenever this electromagnetic wave enters into the waveguide, then due to the total internal reflection it is being reflected from the walls of the waveguide, and there is a internal reflection which happens again and again inside the waveguide, and we are going to observe this internal reflection continuously throughout the length of the waveguide. This is the length of waveguide, which is denoted by L, and there is an internal reflection. By the walls of waveguide. And this electromagnetic wave which is propagating inside the waveguide have some frequency that is denoted by f only, and this frequency in terms of the wavelength is given by c over lambda, where lambda is nothing but wavelength and c is the velocity of light in vacuum. So c is velocity of light in vacuum. Now, whenever this electromagnetic wave enters into the waveguide, then they have some wavelength also, and we can resolve this wavelength into two components. So here is the vertical component, that is perpendicular component also, and it is denoted as lambda n, where n represents the normal component, and there is a parallel component also. So this is a parallel component that is denoted by lambda p, where p stands for parallel and n stands for normal, and here is an angle that is denoted by theta. So the two components are lambda n, which represents normal component to the wall of waveguide, and the second component lambda p represents parallel component to the wall of waveguide. Where this lambda n component is given as lambda over cos theta, and this parallel component, that is lambda p, is given as lambda over sin theta. So we can say that the wall of waveguide will not allow the electromagnetic wave to go outside. That's why it is known as waveguide. And theta is nothing but angle of incidence of the electromagnetic wave inside the rectangular waveguide. So this is all about the basic introduction about rectangular waveguide. If you like my videos, then do subscribe my channel and please hit the like button. Thank you.